Have you ever noticed something so ordinary that you stopped questioning it? An apple falls. A planet circles a star. Light bends around a galaxy. Electrons dance inside an atom. To us, these seem like different events, happening in different places, separated by unimaginable distances and scales. Yet hidden beneath them is something astonishing. They all obey equations. Not approximately. Not most of the time. Every single time. A single equation written on a sheet of paper can predict the motion of a planet billions of kilometers away. Another can describe the behavior of an electron smaller than anything our eyes could ever see. Another explains why stars shine. Another predicts black holes decades before anyone observes them. Again and again, nature behaves as though it is following mathematics. Not merely inspired by it, not loosely resembling it, following it with extraordinary precision. This is so familiar that we rarely pause to appreciate how strange it truly is. Imagine discovering a book written in a language no one has ever taught you. You begin reading random pages, and somehow the words describe tomorrow's weather, the tides of the oceans, the birth of distant stars, and the path of every falling leaf. Eventually, you would stop asking what the book says. You would begin asking a far stranger question. Who wrote this language? Physics has found itself asking a remarkably similar question. For more than 4 centuries, every time humanity has looked deeper into nature, mathematics has been waiting. Waiting inside falling stones. Waiting inside magnets. Waiting inside light. Waiting inside atoms. Waiting inside the fabric of space and time itself. It's almost as if the universe has been speaking mathematics long before anyone was here to understand it. But why? Why should reality obey equations at all? This is not asking why scientists use mathematics. That answer is simple. Mathematics is our language for describing patterns. The real mystery lies elsewhere. Why are those patterns there in the first place? Why does gravity follow an inverse square law instead of an inverse cube law? Why do electric fields spread according to precise equations? Why do waves interfere with exact mathematical regularity? Why does every electron in the observable universe respond identically to the same equation? Nothing in logic demands that reality should behave this way. One can easily imagine a universe where gravity changes every Tuesday, where atoms form differently in different galaxies, where light travels at one speed today and another tomorrow, where 2 identical experiments produce entirely unrelated results. Such a universe would not violate logic. It would simply lack mathematical order. Our universe is not like that. Instead, it displays an almost unsettling consistency. The same equations that describe light in a laboratory on Earth also describe light that began its journey over 13 billion years ago. The same mathematics that predicts the orbit of our moon also predicts the motion of galaxies containing trillions of stars. Again and again, nature behaves as though it recognizes mathematical relationships. Albert Einstein once expressed his amazement with remarkable honesty. The eternally incomprehensible thing about the world is its comprehensibility. It's an extraordinary sentence. Einstein was not celebrating human intelligence. He was expressing surprise that the universe allows itself to be understood at all. Perhaps the greatest mystery in science is not that we have unanswered questions, it is that we have answers. Consider how improbable this really is. The human brain evolved on a small, rocky planet. Its ancestors survived by recognizing predators, finding food, and remembering safe paths through forests. Nothing about evolution required the ability to understand neutron stars. Nothing required the invention of tensor calculus. Nothing required quantum field theory.
Yet somehow the same mind capable of throwing a stone became capable of calculating the age of the universe. How? Some philosophers have argued that mathematics is merely a convenient invention, a powerful tool created by humans.
After all, nobody has ever touched the number 3. No one has photographed the square root of 2. Numbers seem to exist only inside thought. If that were true, then physics would become deeply puzzling. Why would an invented language describe an uninvented universe with such astonishing precision? Suppose someone invents the rules of a board game. Naturally, those rules govern the game. But nobody invented gravity. Nobody designed electrons. Nobody programmed the stars. Long before human beings existed, galaxies collided, black holes merged, atoms formed, light crossed expanding space. If mathematics is merely our invention, then reality somehow began obeying our invention billions of years before we appeared. That seems backwards. The Nobel Prize-winning physicist Eugene Wigner called this the unreasonable effectiveness of mathematics in the natural sciences. He deliberately chose the word unreasonable, because from a philosophical perspective, it truly is. There is no obvious reason abstract symbols written on paper should predict the behavior of objects scattered across the observable universe. Yet they do, again and again and again. The deeper physicists explored, the stranger the relationship became. Isaac Newton did not merely describe falling apples. He wrote an equation that explained the motion of the moon. The same mathematical relationship governed both. Suddenly, Earth and the heavens were no longer separate realms. One equation united them. More than 2 centuries later, James Clerk Maxwell wrote 4 elegant equations describing electricity and magnetism. At first glance, they seemed like nothing more than mathematical expressions. Yet hidden inside them was a surprise no one expected: light. Without ever trying to explain light itself, Maxwell's equations predicted that electromagnetic waves must travel at a specific speed. When that speed was calculated, it matched the measured speed of light almost perfectly. An equation had predicted something nature had been doing all along. Mathematics had revealed a truth before direct observation fully confirmed it. This was not an isolated success. It became a pattern. Again and again, equations seemed to know more about reality than the scientists who wrote them. Paul Dirac discovered that his relativistic equation describing the electron possessed an unexpected solution: a particle with the same mass as the electron but opposite electric charge. No one had ever seen such a particle. Many believed the mathematics had gone wrong. Dirac trusted the equation. Years later, the positron was discovered experimentally. The mathematics had been correct. Reality had quietly been waiting to catch up. This happened so often that physicists gradually developed an unusual habit. When an equation predicts something strange, they no longer dismiss it immediately. Instead, they ask whether nature has simply not revealed it yet. Black holes, gravitational waves, antimatter, the Higgs boson, all appeared first inside mathematics. Only later did they appear inside telescopes and particle detectors. It is difficult to overstate how astonishing this is. Imagine solving a crossword puzzle and accidentally discovering the existence of an undiscovered island. That would seem impossible. Yet something very similar has happened repeatedly throughout the history of physics. Equations have pointed toward pieces of reality long before human eyes could confirm them. Why? Why should symbols manipulated by the human mind possess this extraordinary power? Are equations merely describing reality, or are they revealing something deeper about what reality actually is? That question has quietly followed physics for centuries. And with every discovery, instead of disappearing, it has only grown larger. Some mysteries become smaller as science advances. This one has done the opposite. Every great discovery has made it more difficult to explain why mathematics works so well. Galileo Galilei sensed this long before modern physics existed. Standing beneath the same sky we see today, he wrote a sentence that would echo through the next 400 years. "The universe is written in the language of mathematics." It is one of the most famous quotations in the history of science. But notice what Galileo did not say. He did not say mathematics is useful. He did not say mathematics is convenient. He said the universe is written in it. That is a far stronger claim. Imagine walking into an ancient library filled with books written in a language you have never seen before. At first, the symbols appear meaningless. Then, slowly, patterns emerge. Certain words repeat, sentences follow structure, entire chapters reveal hidden order. Eventually, you realize something remarkable. The language existed long before you arrived. You did not create it. You merely learned to read it. For many physicists, mathematics feels exactly like that. The equations are not invented from nothing. They're uncovered. Each generation simply learns to read a little more of the universe's language. But this raises an uncomfortable question. If mathematics is discovered rather than invented, where was it before anyone discovered it? Did the equation describing gravity somehow exist before Newton? Did Maxwell's equations exist before Maxwell? Did Einstein's field equations already describe curved spacetime before Einstein was born? Most people instinctively answered no. After all, equations are written in notebooks. They're printed in textbooks. Surely they begin when someone writes them down. Yet the events those equations describe were already happening. The Earth orbited the Sun for billions of years before Newton wrote a single symbol. Stars fused hydrogen long before quantum mechanics explained how. Black holes bent spacetime long before Einstein imagined them. Nature was already following relationships that no human had yet recognized. This distinction is subtle, but it changes everything. Newton did not create gravity. He discovered a mathematical relationship that gravity had always obeyed. Maxwell did not invent electromagnetism. He revealed its hidden structure. Einstein did not manufacture spacetime. He uncovered a deeper description of something that had always existed. Again and again, physics behaves less like invention and more like archaeology. Scientists are not constructing reality. They are excavating it. Each equation is like brushing away another layer of dust from an ancient monument that has been standing since the beginning of the cosmos. The monument was always there. We simply could not see it clearly. This way of thinking became known as mathematical realism. According to this view, mathematical structures exist independently of human minds. Just as mountains exist whether anyone climbs them, mathematical truths exist whether anyone proves them. The number pi would still relate the circumference of every circle to its diameter, even in a universe without observers. Prime numbers would remain prime. Triangles would still contain angles summing to 180 degrees in flat space. Humanity would simply never know. Many mathematicians have described their work in exactly these terms. They do not speak of creating mathematics, they speak of finding it. The British mathematician G.H. Hardy once remarked that a mathematician, like an explorer, discovers patterns that are already there. This language is remarkably common. Even today, researchers often describe beautiful proofs as discoveries rather than inventions. Yet another school of thought reaches the opposite conclusion. Perhaps mathematics exists only because minds exist. Perhaps numbers are nothing more than concepts, useful concepts, powerful concepts, but concepts nonetheless. According to this view, mathematics resembles music. Music can describe emotion with astonishing depth, yet nobody imagines symphonies floating through empty space before composers existed. Perhaps equations are similar, elegant creations of intelligent minds. If so, then mathematics tells us more about ourselves than about reality. At first, this idea sounds reasonable, until physics begins making predictions. Because here is the difficulty. Music does not predict undiscovered planets. Poetry does not predict antimatter. Language does not predict black holes. Yet mathematics repeatedly predicts things no one expected. That changes the conversation completely. Imagine an explorer drawing a map of a coastline. While calculating the next section, the map suddenly reveals an island no one has ever visited.
Years later, sailors arrive exactly where the mathematics indicated and find the island waiting. How many times would that need to happen before you began wondering whether the map contained something deeper than imagination? Physics has lived through this experience again and again. One of the most beautiful examples appeared in the 19th century. James Clerk Maxwell was not searching for radio waves. In fact, radios didn't even exist. His goal was much simpler. He wanted to unify electricity and magnetism into a single mathematical framework. After years of work, he reduced an enormous collection of experimental observations into 4 elegant equations. At first glance, they looked almost disappointingly simple. A few symbols, a handful of derivatives, nothing that suggested they would transform civilization. But mathematics often whispers before it shouts. When Maxwell analyzed his own equations, something extraordinary emerged. They predicted waves, not water waves, not sound waves, waves of electric and magnetic fields traveling together through empty space. Even more astonishing, those waves possessed a definite speed. When Maxwell substituted the known electrical and magnetic constants into his equations, the calculated speed matched the measured speed of light. He realized something breathtaking. Light itself was an electromagnetic wave. No experiment had told him this directly. The mathematics had. Nature had hidden light inside equations waiting to be solved. Think about what that means. The universe had been producing sunlight for billions of years. Stars illuminated galaxies. Nebulae glowed across cosmic distances.
Every sunrise in Earth's history depended on electromagnetic waves, yet the mathematical description already contained that truth before humanity fully understood it. Equations were not merely recording observations, they were revealing unseen connections. This became one of the defining moments in the history of science. For perhaps the first time, mathematics appeared not simply as a language for organizing knowledge, but as a guide leading beyond knowledge itself. Albert Einstein experienced something remarkably similar. His theory of general relativity replaced Newton's picture of gravity with an entirely different vision. Gravity was no longer a force pulling objects together. Instead, matter and energy curved space-time, and objects followed those curves. It was an astonishingly abstract idea. So abstract, in fact, that many physicists initially doubted whether the mathematics corresponded to anything real. But Einstein trusted the equations. They implied that massive objects should bend light itself. At the time, this seemed almost absurd. Light has no mass. How could gravity affect it? Yet during the solar eclipse of 1919, observations confirmed precisely what Einstein's equations predicted. Starlight passing near the sun shifted exactly as the mathematics required. Again, reality behaved as though it had been quietly following equations all along. The pattern kept repeating, again, and again, and again. By now, physicists had begun asking a different question. Not, can mathematics describe nature? That answer appeared increasingly obvious. Instead, why does nature seem eager to reveal itself through mathematics? Those are profoundly different questions. The first belongs to physics, the second borders on philosophy, and perhaps even something deeper. Because once you begin asking why equations work, another mystery quietly appears behind it. What exactly is an equation? Most people see equations as collections of symbols, letters, numbers, equal signs. But to a physicist, an equation is something far more remarkable. It is a statement that certain relationships never change. No matter where you go in the observable universe, those relationships remain. Gravity may become weaker with distance. Temperatures may rise or fall. Stars may explode. Galaxies may collide. Yet the relationship itself endures. The equation survives. It is as though the universe allows countless events to unfold while refusing to alter the rules connecting them. That kind of permanence is extraordinary. Almost everything in nature changes.
Mountains erode, stars die, atoms decay, even space itself expands, yet the equations describing those processes remain untouched. Why? Why should relationships remain fixed while everything they describe evolves? This question leads directly to one of the deepest ideas ever discovered in physics, an idea so fundamental that it quietly explains why equations possess the power they do. It begins with something that seems almost too simple to matter: symmetry. And as generations of physicists would discover, symmetry is far more than beauty. It may be the hidden reason the universe can be described by equations at all. Long before physicists understood atoms, long before they knew about galaxies, long before anyone imagined curved spacetime or quantum fields, people already recognized symmetry. A butterfly, a snowflake, a crystal, the human face. Symmetry seemed to belong to beauty. Artists admired it. Architects relied upon it. Nature displayed it everywhere. For centuries, it appeared to be little more than an aesthetic preference. Then, physics discovered something astonishing. The universe does not preserve symmetry because it looks beautiful. It preserves symmetry because reality itself depends on it. To understand why equations exist, we first need to understand what physicists mean when they use the word symmetry. It is not quite the same meaning as the everyday meaning. Imagine drawing a perfect circle on a piece of paper. Now rotate the paper. 10 degrees, 90 degrees, 180 degrees. The circle never changes. Its appearance remains identical. Something about it has stayed invariant. That invariance is symmetry. Now imagine standing in an empty room and performing the same experiment tomorrow instead of today. The laws governing a swinging pendulum have not changed. Gravity has not become weaker overnight. Light has not slowed down. Physics behaves exactly as it did yesterday. Time has shifted. The laws have not. That too is symmetry. Or imagine performing the same experiment in London, then repeating it on the moon. Different surroundings, different gravity, different atmosphere, yet Maxwell's equations remain the same. Quantum mechanics remains the same. The mathematical framework survives the journey. Again, symmetry. At first, these examples seem almost trivial. Of course the laws should stay the same. Why wouldn't they? But pause for a moment. There is no logical necessity that nature behave this way. Reality could have been wildly inconsistent. Gravity might have depended on the direction you faced. North could have obeyed one equation, south another. Electrons might have carried different charges every million kilometers. The speed of light might have drifted from century to century. None of those possibilities violate logic. They simply do not describe our universe. Instead, nature behaves with extraordinary consistency. The equations remain unchanged while the circumstances change around them. That consistency is one of the greatest clues physics has ever discovered. In the early 20th century, a young German mathematician named Emmy Noether asked a deceptively simple question. Suppose nature possesses these symmetries. What follows from them? Many believed the answer would be, not very much. After all, symmetries sounded like geometry. Interesting, elegant, perhaps useful. Certainly not fundamental. They were wrong, very wrong. In 1918, Noether proved one of the deepest theorems in the history of science. Her result was so powerful that nearly every branch of modern physics rests upon it today. The theorem can be summarized in a single astonishing sentence. Every continuous symmetry corresponds to a conservation law. It sounds abstract, almost disappointingly simple, yet hidden inside those words lies the architecture of reality. Take time. The laws of physics do not change from one moment to the next. That symmetry produces conservation of energy. Energy cannot simply appear from nowhere, nor can it disappear into nothingness. Now consider space. The laws remain the same whether an experiment is performed here or 1,000 kilometers away. That symmetry gives us conservation of momentum. Now rotate an experiment. Turn it in any direction. If the laws remain unchanged, angular momentum is conserved. 3 familiar conservation laws, 3 symmetries, 1 theorem. It was an extraordinary revelation. Things physicists had previously considered independent suddenly became connected by mathematics. Conservation was no longer an isolated observation. It became the inevitable consequence of symmetry. This transformed the way scientists viewed equations.
The equations were not arbitrary recipes. They reflected deeper invariances built into reality itself. Imagine listening to an orchestra. At first, you hear individual instruments, violins, cellos, flutes, trumpets. Then someone hands you the musical score. Suddenly, what sounded like separate melodies becomes one coherent structure. Noether's theorem was like discovering the score behind the universe. Conservation laws, particle motion, forces, they were all expressions of something deeper. Symmetry. Albert Einstein immediately recognized the significance of Noether's work. General relativity had been facing difficult mathematical problems involving conservation of energy. Noether's theorem clarified relationships that even Einstein had struggled to express. He praised her work with extraordinary admiration. Coming from Einstein, such praise carried immense weight. Today, Noether's theorem is considered one of the most profound achievements in mathematical physics. Yet, despite its importance, very few people outside physics have heard her name. Perhaps because the theorem is not dramatic. It produces no explosions, no colorful photographs, no famous telescope images. Instead, it quietly explains why the universe possesses reliable rules. And once you see it, it becomes difficult to imagine physics without it. But symmetry itself raises another mystery. Why should reality care about symmetry? Why should changing location, or time, or direction leave the equations untouched? Again, physics can describe the pattern. It cannot fully explain why the pattern exists. The deeper we investigate, the more mathematics resembles a chain. Each answer is linked to another question. Pull one link and another emerges. By the middle of the 20th century, physicists began noticing something even stranger. Symmetry was everywhere. Not only in gravity, not only in electromagnetism. It appeared inside the atomic nucleus, inside quantum mechanics, inside particle physics. Sometimes it was obvious. Often it was completely invisible. Certain symmetries could not be seen directly, yet the equations demanded their existence. One remarkable example emerged from electromagnetism. Imagine carrying a charged particle through space. You can describe its electric field using quantities called potentials. Curiously, those potentials can be changed in specific ways without altering any observable measurement. Different mathematical descriptions, identical physical reality. This hidden freedom became known as gauge symmetry. At first glance, it looked like little more than mathematical bookkeeping, a convenient trick. Many physicists treated it exactly that way. But over time, something astonishing happened. Gauge symmetry refused to remain a trick. Every successful theory describing fundamental forces seemed to depend upon it. Electromagnetism, the weak nuclear force, the strong nuclear force. Again and again, gauge symmetry appeared at the heart of the equations. Eventually, physicists reached an astonishing conclusion. Perhaps forces themselves are consequences of symmetry. That idea overturned centuries of intuition. For thousands of years, people believed forces were primary. Objects attracted, objects repelled. Forces simply existed. Modern physics quietly reversed the picture. Perhaps symmetry comes first, and forces emerge from it. Think carefully about how radical that idea is. It suggests gravity, electricity, magnetism, even the interactions inside every atom may not be fundamental ingredients. They may be consequences of deeper mathematical relationships. The universe begins looking less like a machine built from objects and more like a structure built from principles. Principles expressed through equations, principles protected by symmetry. Principles that appear astonishingly indifferent to where or when the universe unfolds. Once again, the equations seem less like human inventions and more like windows into something ancient, something woven into reality long before stars ignited. But symmetry is only part of the story, because something equally important happens when symmetry breaks. Surprisingly, many of the features that make our universe possible do not arise from perfect symmetry. They arise because symmetry was lost. And that loss may explain why the universe looks the way it does today. Imagine placing a perfectly round pencil upright on its tip. For a brief moment it stands, balanced. Every direction is equally possible. There is no preferred side. The situation is perfectly symmetrical. Then, almost imperceptibly, the pencil begins to lean. A tiny vibration, a microscopic fluctuation, nothing dramatic, yet within seconds the symmetry is gone. The pencil falls, north, south, east, west. The laws governing the pencil never changed. Only the state of the system changed. Physicists call this spontaneous symmetry breaking. The symmetry exists in the underlying rules, but reality settles into one particular outcome. This idea appears so often in modern physics that it has become impossible to ignore. Perhaps the universe itself began in a similar condition. In the earliest fraction of a second after the Big Bang, temperatures were so unimaginably high that distinctions we see today may not have existed at all. Gravity, electromagnetism, the strong nuclear force, the weak nuclear force. Today they appear completely different. One shapes galaxies, another holds atoms together, another governs radioactive decay. Yet many physicists suspect these forces were once united, different expressions of a deeper symmetry. As the universe expanded, it cooled, and like the falling pencil, the symmetry broke. The equations remained, but reality selected one possibility from many. This was not an accident in the ordinary sense. It was a phase transition. We encounter phase transitions constantly. Water freezes into ice, steam condenses into liquid, molten rock hardens into stone. The microscopic rules governing water molecules remain the same throughout, yet entirely new properties emerge as temperature changes. The universe may have experienced similar transitions on a cosmic scale, not involving water, but involving the very structure of reality itself. If that sounds abstract, imagine standing in a vast snow-covered field. Fresh snow has fallen overnight. The surface is perfectly smooth, no footprints, no paths. Every direction appears identical. Then one traveler begins walking. A trail forms. Soon others follow it. Eventually, the once symmetric landscape contains preferred routes. The field did not command anyone to walk there. The first path simply became established. Something similar may have happened during the earliest moments of the universe. The laws permitted many possibilities. Reality settled into one. This idea became especially important after physicists proposed the existence of the Higgs field. For decades, one question had stubbornly resisted explanation. Why do elementary particles possess mass? The equations describing the electroweak force worked beautifully, provided every particle had no mass. Unfortunately, the real universe disagreed. Electrons have mass. Quarks have mass. The W and Z bosons have mass. Somehow, nature had chosen a universe different from the perfectly symmetric mathematical version. The solution arrived through spontaneous symmetry breaking. According to the Higgs mechanism, the Higgs field fills all of space. Not most of space, all of it. Even the emptiest regions between galaxies are permeated by this invisible field.
Particles moving through it interact differently. Some interact strongly, some weakly, some almost not at all. Those interactions appear to us as mass. This is one of the strangest ideas in modern science. Mass is not necessarily an intrinsic property carried by particles. It may emerge from an interaction with a field that quietly exists everywhere. Peter Higgs and several other physicists proposed this mechanism during the 1960s. For nearly half a century, it remained a mathematical prediction. No one had ever observed the Higgs boson. Some doubted it would ever be found. Then, in 2012, the Large Hadron Collider revealed evidence of the particle with extraordinary statistical confidence. Once again, the equations had pointed toward reality long before experiments confirmed it. The pattern had repeated. Mathematics first, observation second. It had happened with antimatter. It had happened with gravitational waves. It had happened with black holes. Now it happened with the Higgs boson. Each success strengthened an uncomfortable suspicion. Perhaps mathematics is not simply describing reality. Perhaps reality itself possesses mathematical structure. This possibility has fascinated physicists and philosophers for generations. Because if equations repeatedly predict unseen pieces of the universe, then maybe equations are not merely tools. Maybe they are glimpses of something more fundamental. But another mystery was quietly emerging. The equations seemed almost too successful. Consider the orbit of Mercury. For decades, astronomers noticed a tiny discrepancy. Newton's equations predicted Mercury's orbit with astonishing accuracy, yet not perfect accuracy.
The closest point in Mercury's orbit drifted, only a tiny amount, 43 arcseconds per century, an incredibly small deviation. Many believed another unseen planet was causing the effect. Astronomers searched. Nothing appeared. Then Einstein published general relativity. Without adding new planets, without modifying observations, his equations naturally produced the missing 43 arcseconds. The discrepancy vanished. The mathematics had reached deeper than Newton's. Nature had not changed. Our description had. This illustrates one of the most remarkable features of physics. Equations are not static. They evolve. Not because reality changes, but because understanding deepens. Newton's laws remain extraordinarily accurate for everyday life. Engineers still use them. Space agencies still use them. Yet Einstein revealed they were part of a larger mathematical framework. This has happened repeatedly throughout history. Each generation discovers equations that explain a wider range of phenomena. Older equations are rarely discarded completely. Instead, they become approximations, special cases, like zooming out from a map. A neighborhood map is not wrong, it simply does not reveal the entire continent. The deeper mathematics always contains the simpler mathematics. That is an extraordinary pattern. Nature seems organized in layers, each layer connected through mathematics. Classical mechanics emerges from quantum mechanics under familiar conditions. Newtonian gravity emerges from general relativity when gravitational fields are weak. Thermodynamics emerges from statistical mechanics. Wave optics emerges from electromagnetism. Again and again, physics uncovers deeper equations from which familiar ones naturally arise. This hierarchy raises another profound question. How deep does it go? Is there a final equation, a mathematical description from which every other law of nature emerges? For over a century, physicists have searched for exactly that. Einstein devoted the final decades of his life to finding a unified field theory. He believed gravity and electromagnetism should emerge from one deeper mathematical structure. He never succeeded. After Einstein's death, the search continued. The Standard Model unified enormous portions of particle physics with astonishing precision. General relativity described gravity on cosmic scales. Both theories became spectacularly successful. There was just one problem. They refused to fit together. Quantum mechanics governs the microscopic universe. General relativity governs the large-scale universe. Individually, they are masterpieces.
Together, they resist unification. Whenever physicists attempt to combine them under extreme conditions, inside black holes or during the first instant after the Big Bang, the mathematics begins to fail. Equations that work beautifully elsewhere suddenly produce infinities. Predictions lose meaning. It is as though the universe is quietly telling us, "You have not reached the deepest layer yet." That realization has driven generations of physicists toward an extraordinary dream: a single mathematical framework, one set of principles, one structure from which gravity, quantum mechanics, particles, forces, space, and time all emerge naturally. Some call it the theory of everything. The name sounds ambitious, perhaps impossibly ambitious.
But notice what physicists are really searching for. Not one final experiment, one final equation. And perhaps that is the strangest clue of all. When science reaches its deepest questions, it does not search for larger telescopes, or faster rockets, or more powerful microscopes. It searches for mathematics. Why? Why should the deepest secrets of reality always seem to hide behind equations? The answer may lie in an idea so radical that it changes not only how we understand mathematics, but what we mean by reality itself. Why does the universe run on equations at all? For centuries, this question belonged almost entirely to philosophers. Physicists were too busy discovering new laws. There were planets to predict, atoms to understand, stars to explain. The success of mathematics was simply accepted. It worked. That seemed enough. But eventually the success became impossible to ignore. The equations were not merely accurate, they were astonishingly accurate. When physicists calculate the magnetic moment of the electron using quantum electrodynamics, theory and experiment agreed to more than 10 decimal places. Imagine measuring the distance from New York to Tokyo and making an error smaller than the width of a human hair. That is the level of agreement modern physics sometimes achieves. Richard Feynman called it one of the greatest achievements in the history of science. How can reality be predicted with such precision? Not approximately, not statistically, digit after digit after digit. Nature agrees. It is almost unsettling because the universe does not have to cooperate this perfectly. Suppose you threw 1,000 dice. You might predict the average outcome, but predicting every individual roll would be impossible. Yet physics often behaves as though the universe has already decided every rule in advance. Not rigidly, but consistently. Every photon, every electron, every atom, they all respond to the same mathematical relationships, billions upon billions of times each second, without exception, without hesitation. The equations never need correcting, only our understanding of them does. That distinction matters. Scientists do not rewrite the laws of nature, they rewrite textbooks. The universe itself continues exactly as before. Perhaps the most remarkable example comes from one simple equation, Einstein's field equation. At first glance, it appears almost impossibly compact, just a handful of symbols, a few tensors, one equality. Yet hidden inside that mathematical expression are black holes, gravitational waves, expanding space, the bending of light, the evolution of the universe itself. Entire cosmic histories emerge from a single relationship. How can so much reality fit inside so little mathematics? It almost feels backwards. One might expect reality to be infinitely more complicated than an equation. Instead, the equation often appears simpler than the universe it describes. Why? The physicist John Archibald Wheeler once summarized this mystery in 4 words: it from bit. His idea was radical. Perhaps information is more fundamental than matter. Perhaps particles, fields, even space-time emerge from deeper informational rules. At the time, many considered the proposal speculative. Today, information has become central to modern physics. Black hole thermodynamics, quantum computing, entanglement, the holographic principle.
Again and again, information appears where physicists least expected it, and information itself is mathematical. Bits, states, relationships, patterns, not physical objects, abstract structures. The boundary between mathematics and reality begins to blur. The more deeply we investigate, the harder it becomes to say where one ends and the other begins. This brings us to one of the boldest ideas ever proposed. In 2007, the cosmologist Max Tenmark suggested something extraordinary. Perhaps the universe is not merely described by mathematics. Perhaps it is mathematics. Not metaphorically, literally. According to his mathematical universe hypothesis, every consistent mathematical structure exists in the same sense that our universe exists. Our cosmos is simply one such structure. In this picture, electrons are not obeying equations, they are expressions of equations. Space is mathematics, time is mathematics, gravity is mathematics. Reality and mathematics become identical. It is a breathtaking proposal.